This is one of my favorite discussions to deal with set theory. And as you can see here, this is what the discussion is going to be about. I sometimes like to jokingly call this the Seinfeld video. If you've ever seen Seinfeld, you may know what Seinfeld is about. It's famously about nothing. So this particular video is going to be about nothing and the properties of nothing, or as we mathematically call it, we're going to look at the properties associated with the empty set, which are kind of interesting. Now, a little bit of review here. If we have two sets, A and B, that are disjoint, like these two are, then we can say that A intersection B is equal to the empty set, which we can represent this way, or we can represent it with the null character. We call it either the empty set or the null set. Do remember that these things are not equal to this. Now let's address something again that we talked a little bit about before. Is that null set a subset of A? Well, we found that the answer was yes, and we did it by doing a proof by contradiction. Basically, we said, suppose not. Suppose the empty set is not a subset of A. Well then, that would mean that there exists something in the empty set that is not in A. But we can't have an element in the empty set because it's empty. This is a contradiction, so what we get is that the empty set is a subset of A. Now what I'd like you to notice now, there we are, there's the whole thing. But X is not an element of the empty set since X is empty. That's a contradiction, so the empty set is a subset of A. What I'd like you to notice is that the contents of the set A do not matter. So what that tells you is that the null set is a subset of every set, which was very helpful when we were doing the problems dealing with power sets. Now I'd like to ask the question, is every empty set the same? Like suppose we had an empty set A, and it's the set of no apples, and an empty set B, which is the set of no baseballs. Are these two empty sets the same thing? Well, are they equal? Let's take a look at this. Let's suppose that both of these empty sets are indeed empty, which means they have no elements. Now, how do you prove that two sets are equal? Well, what I'd have to do is show that everything in the set of all apples is a subset of everything that's a set of no baseballs. Is everything that is in here? Well, yes, because there's nothing in here. Does it work the other direction? Is the set of no baseballs a subset of the set of no apples? Well, yes, it is. And since this is a subset, this null set is a subset of this one, and this null set is a subset of this one, then you know that the two subsets have to be the same, and there is only one null set. This kind of reasoning by a contradiction is very helpful for us in proving some properties of sets. So how do you show a set is empty? You almost always do it by contradiction. Suppose I wanted to prove this property of the empty set, that if I take a set D, intersect it with the null set, that I get the null set. If we wanted to show that this is a true statement, we need to show that this set D intersection the null set has no elements. How are we going to do that? Well, let's suppose just the opposite. Suppose X is an element of D intersection the null set. Well, what does it mean to say it's in the intersection of D and the null set? Then we know that X is an element of D and X is an element of the null set. But having X an element of the null set is a contradiction. And since that's a contradiction, this statement has to be true. This leads us, if we do these proof by contradictions, to some really interesting properties that we would have with the null set. If I take any set and do a union with the null set, I get the original set back again. And we just proved that if I take any set and do an intersection with the null set, I get the null set. What if I take a set and intersect it with the complement? If I intersect the set with its complement, I get the null set. But if I take a set and do a union with its complement, I get the universe. What is the complement of the universe? It's the null set. And what is the complement of the null set? Why, it's the entire universe. Interesting properties, and mainly you show these things by doing element-wise proofs and proofs by contradiction. Those are the main takeaways I want you to have from section 6.2.